Good morning, students. So today we will discuss about experiments on subgrade soil. So we know the subgrade soil forms the foundation for the payments. Either it is flexible payment or rigid payment, it forms the founding material. So the selection of subgrade material should be made very judiciously, because once if you lay a very wrong subgrade or a very weak subgrade, and once payment is constructed, it's very difficult to correct the again subgrade properties. So the selection of subgrade soil involves some particular test such that the soil will be properly classified, categorized into how its behavior will be over long term. Right? For that particular selection or characterization, we do some test, right? Commonly in the field of payments, what we call as characterization test. Characterization test. So among this, right, normally we do, most important thing is Atterberg limit. Atterberg limits test. Then we do Proctor test, right? Then we have California bearing ratio. And then we have free swell index test. Today we will cover these four tests in this laboratory video, and remaining tests will be covered in the subsequent videos. So now we will see the first two tests, the Atterberg limits and the free swell index test, right? So what is Atterberg limits? So what happens in the case of soil? When soil comes in contact with water, the soil may tend to expand, right? It can bulk its volume. Similarly, when the water goes away, it can shrink. So now these characteristics will give an indication how the soil will behave in the long term, right? So to classify the soil behavior, right? So we use some particular limits, what we call as, right, shrinkage limit, plastic limit, and liquid limit. Now these particular limits in terms of water content will indicate the soil behavior. Now let's say, if you see this particular figure here, so this is a volume, and this is drying stage, and this is a wetting, right? So in this solid phase, the volume almost remains constant. But now when there is amount of wetting, you can see there is a volume increase in the semi-solid phase. The soil which was in solid form becomes semi-solid. Then again, if you add more water, it becomes plastic, right? It becomes sticky. And then when you add much more water, it tends to flow, right? It can easily start flowing, where it is called as liquid limit. Now, depending on the water content, we have three kind of limits: plastic shrinkage limit, plastic limit, and liquid limit. Now, for a payment subgrade material, now the plastic limit and liquid limit are two very important properties. So, now what is plastic limit? The plastic limit is a minimum water content, right? There is a wetting and there is a water content. Minimum water content beyond which the soil turns out to be plastic. Now, plastic means what? If you deform, that it can't return its original shape back. So it will deform permanently. It becomes sticky and very difficult to work with it. Similarly, what is liquid limit? The liquid limit is a minimum water content, right, where the soil has tendency to start flow. Right? It can start flowing beyond when the water can increase beyond liquid limit. So this way, the PL and LL are most commonly used in soil test in any highway engineering soil selection. So other important property is the difference between the LL and PL, what we call as plasticity index. So this PI is basically difference which indicates the range of water content where the soil remains plastic. If you see this particular range, let's say if this range is broader, then what happens? For a broader water content range, the soil remains plastic. Similarly, if this range is narrower, then what happens? For a narrow water content, the soil remains plastic. That means what? For a given soil, we always try to see that the PI is less. So if PI is less, so what indicates? The soil is plastic over a very small range of water content. If PI is too large, then the soil is in plastic state for a broader range of water content, which is not preferable for highway pavements. So that's why if you see most of the highway guidelines, you might have seen that the pH, preferably pH for a higher material should be less than 6%. Sometimes even pH should be less than 4%. So now let's say if the pH is too high, normally let's say liquid limit is 30 and plastic limit is 15, then pH is 15%, right? In that case, one of the methods to reduce pH is through stabilization. So by using lime or cement stabilization, we can reduce the pH and reduce the range at which the soil will tend to remain in a plastic state. So now, sometimes what happens, let's say if we take a sandy soil, right, those soils are non-plastic. So we will see how to determine liquid limit and plastic limit through simple experiment, right? Now the other important test is freeze well index. It is called as FSI. Now we all know the black earth on soil and any soil that has more clay content tends to expand. When there is expansion in the subgrade level, the whole pavement will try to expand or heaving. What we call as heaving. Now when this heaving or expansion happens, cracks can be seen in the top layers, in the bituminous layer or any bound layer, we can see cracks. So now we should determine how determine the soil tendency to expand by some simple field test or also lab test. For that we conduct freeze well index test. It is what we do basically. We take normal tube, a glass tube, then we add soil up to let's say X level. We have graduations in this particular tube, let's say, and up to X level you add soil and you add kerosene. So why do we add kerosene? In the kerosene, the soil doesn't tend to expand. Similarly, we take one more tube and then add same soil up to same level. But in this we add water, right? So we note down the both levels, X and X are same in both tube, but one is having kerosene, other is having water. Now you leave this particular tube undisturbed for 24 hours. This one day you leave it, we can close this tube, right? We can close this with a stopper, close this, and then you leave it undisturbed. After 24 hours, what happens? There will be a slowly, wherever there is a the tube containing water, the soil level will increase. That is, the soil tends to expand when it comes to contact with the water. If it has more amount of clay content in the soil, then the water molecules can go between the clay particles and increase the volume. So this way, there can be a bulking or increase in the volume of soil which has more amount of clay. If you see here, initially it was X, now it has come to X plus Y. Now Y is the amount which has expanded. Now you can find just the FSI simply by FSI will be equal to Y by X into 100. Normally, if you see black cotton soil, right, all these soils should be having FSI more than 50%. If it is more than 50%, it's not a good soil for a pavement construction. Even whenever let's say FSI is more than 25 or so, 20%, it can be quite risky to use those kind of soils in the pavement subgrade. So preferably those soils can be removed or they can be stabilized once we see what is the PI value of those soils, so that we have a proper soil characterization test, and then we decide should we go for soil replacement with the borrow soil or should we stabilize with lime or cement. So now we will give a simple demonstration how these tests are conducted in the next video. So now I told about liquid limit and plastic limit. Now both are basically the water content. So we should find the water content at which some particular observation are seen. So for find liquid limit, we use a simple apparatus called as Casagrande apparatus. So this what we do basically is we take a particular soil mass and then we mix with water of known water content. We know the soil mass, we'll add some percent of water and then we fill the whole soil, the wet soil mass in this cup. Then what we do with this standard groove, in this standard groove we make a partition between two in the soil. So we have two parts, one part here, other part here. So once we fill the soil in this mass and then we make a groove, right? What we do, we'll start rotating this, right? Due to this rotation and this cups up and down motion, the soil mass will tend to join together. Now we'll determine how many blows it took for the soil mass to join for the 1 inch length. So now there are two parts. Now they'll start slowly closing. So how many blows it took to join 1 inch will determine. That will note for the given water content and we take some soil mass to find the actual water content. Now next again we'll increase the water content. Again we'll repeat this experiment. So we subsequently do, let's say for different water contents, around 5 different water contents, and then we'll make a plot with number of blows versus the water content. Right? Corresponding 25 blows, we'll find the liquid limit.